Okay, let's talk about the area of a surface of revolution. So, we have talked about the volume of solid of revolution before, where we are taking a curve and we're revolving it around some axis, but what we're finding is the volume of this shape. What we're going to do today is the surface area. And I'm just going to give you a formula. I thought about maybe explaining where this formula comes from, but I think maybe it's best if I just don't try to do that. It looks vaguely like the arc length formula, which is maybe not surprising. Like if I cover this part up, then that's just the length of this curve. So anyway, we're mostly just going to use this formula, and like many applications of integration, this just turns into practice doing integrals. So first of all, there's two forms of this. If I have y as a function of x, I can use this formula, which is the same as this. Like the only difference between this and this is instead of f of x, I wrote y. Instead of f prime, I wrote dy over dx. Same thing. There's also, and by the way, this formula is always revolving around the x-axis. That's all we're going to do for surface areas. This is for if you have x as a function of y, and we have this formula. And again, I wrote this in two different ways. Like g prime is the same as, this would be the derivative of x with respect to y. So like we have we have x as a function of y, so we take the derivative of it. That's what dx over dy means. Anyway, let's use it for something. So this is going to be another one of those examples where we take probably a frustrating amount of work to do something that we should know the answer to, but I like that. We're going to find the surface area of a sphere, and you may, if you have a good memory, you may remember a formula for the surface area of a sphere, but we're not going to use that. We're going to use this formula, so we're going to evaluate an integral. Of course, so this is the top half of a circle. As y is 1 minus x squared. I guess we're about to do a bunch of calculus, so let me write the 1/2 power. And so we're just going to use this formula. So I have y as a function of x, so I'm going to use the first one. So it's going to be an integral from -1 to 1, because that's my limits for x. I'm going to have a 2 pi. In fact, as usual, I can just pull the 2 pi out. I have my f of x, so that's this. And then I have the square root of 1 plus f prime of x squared. So I'm going to fill in that blank with f prime of x. Oh, I forgot to write this is squared. Okay, so we have a little chain rule here. This is 1/2 1 minus x squared to the -1/2 times the derivative of the inside, which is minus 2x. Okay, I can cancel a half with the 2. Now let's simplify this. Okay, I'm mostly going to work underneath the square root here. One plus. Okay. I have something to the -1/2, and it's getting squared, and I multiply powers, so this is going to be 1 minus x squared to the -1. That's when I square that. And then this negative sign goes away because I'm squaring it, and then this x becomes x squared. Okay, making progress. All right, what now? Now, maybe I'll just make this a fraction. Like, this is just like x over 1 minus x squared. Sorry, x squared over 1 minus x squared. It's minus 1 power, just goes on the bottom. And maybe, yeah, I'm really trying to simplify this because the square root is making my life difficult right now. So maybe I would like to have a common denominator. So actually, yeah, let me maybe go off to the side here. What's underneath the square root? That's like 1 minus x squared over 1 minus x squared plus x squared over 1 minus x squared. I'm just getting a common denominator here. And then I add going across, and that's just 1 over 1 minus x squared. Let me rewrite it. Okay, making progress, things are getting simpler, and now something, I mean, it's going to get ridiculously simple. Let me point something out here. This is the square, this 1/2 power is the same as a square root, and over here I see the same exact thing, 1 minus x squared underneath a square root in the bottom. This cancels this, and we just get 1. Look at how simple that got. We went from this, like, look at this. It was 1 this whole time. Anyway. Picking up from there. That was just 1, so antiderivative is just x. So 1 minus negative 1. So I get 4 pi. And of course, that's what we're supposed to get. The formula, for those who didn't remember, the formula for the surface area of a sphere is 4 pi r squared. And our sphere had a radius of 1 because we were taking a circle of radius 1 and revolving it. So we got the right answer, and it actually wasn't that hard. I mean, it definitely would be easier to just remember the formula, but this wasn't that bad. Okay. Let's do another one. So I'm just putting the first sheet back up because I want to show you an example of the second version of this formula, the one where we have x as a function of y. So this time we have x as a function of y, and I drew a picture. The picture isn't really necessary. I just like pictures. This is a sideways parabola opening to the right, and we're going from y equals 1 to y equals 2. So it's like we're taking this piece of the parabola from here to here and revolving it around the x-axis, and then that's the surface area that we're finding. But again, the picture isn't really necessary. We're just using this formula. So I'm going to have the integral. These are limits for y. Y goes from 1 to 2. I've got a 2 pi that I can just write on the outside. And then this is an integral with respect to y. So I'm not going to replace y with anything. I'm just going to write y. Y is just y. And then this is 1 plus this g prime of y, so this is my g of y, so I'm doing the derivative of this, which would just be a 4y. So that's what I've got. Okay, let's do this integral. So there's hardly anything going on right now. I just squared that out, so it's 16y squared. And now we think what to do. Okay, we have learned trig substitutions recently. This looks like maybe we could do a trig substitution, but before I rush into that, let me just think a little bit, and there's something easier. I can just do a regular substitution. I can let w be the thing underneath the square root, and as soon as that idea pops in my head, dw would be a 32y, and I don't care about the 32. What I care about is the y, because I see y right there. So this is going to work. W is this. dw is 32y dy. So this integral becomes 2 pi. Oh, now this is the hardest part. I have to find the w values that correspond to these y values. Well, if y is 1, then I'm getting 17, so 1 plus 16. And then when y is 2, let me show off my math skills. I'm supposed to be good at this, right? 16 times 4 is 64, so I get 65. And then what? Y dy, that's like 1, or yeah, sorry, let me write that, I'll write that over here. 1 over 32 dw, I just need the 1 over 32 to fix this 32. And then that takes care of the y and the dy, and other than that, I've just got square root of w. Okay, here we go. This isn't going to take long. All right, let me pull the 1 over 32 out. So I've got pi over 16. And then, yeah, okay, I can do this all in one step. This is w to the 1/2, and how do I integrate that? I go 2/3 w to the 3/2, right? Because it's w to the 1/2. I increase the power by 1, and I do the reciprocal. 1765, cancel a little bit. So I'm going to have, okay, pi over 24. That's what comes of this. And then I've got 65 to the 3/2 minus 17 to the 3/2. And I'm going to leave it just like that. These square roots don't really simplify, because the 3/2 that's like doing the square root and then cubing it. If I could do the square root of 65 or the square root of 17, then I would be tempted to simplify it more, but let's just leave it like that.